So in the last class, we were discussing the quantization of the gauge field, the electromagnetic field, and we have obtained we obtained in the last lecture that the Hamiltonian for the electromagnetic field will be of this form. It will be summation over k, summation over lambda. Then we will have k dagger lambda a lambda plus h bar. Okay. So as I mentioned, the Hamiltonian was of this form. We started with the following form of the Hamiltonian, which was 1 by h pi, and it was dqx, then 1 by c square a vector dot square plus curl of a square, and we substituted the mode expansion for the vector field for this a dot, because we had the mode expansion for a. From there we calculated a dot, then squared it up. We calculated curl of a, squared it up, and then we integrated over the dx over the spatial volume, which is our integration over volume v. And then if you substitute the normal mode expansion, so Fourier expansion, then you would land up to this result, and we derived this result in the previous lecture. So this completes the quantization of the electromagnetic field, and just as in the case of the real scalar field or the complex scalar field, remember that this is the annihilation operator and this is the creation operator, and you know what the computation relations between them are, and the vacuum is defined by the state. Vacuum of this field theory is defined by the state, which gets annihilated by A. It gets annihilated by A, and you create particles by using the creation operator A diagram. And here, this summation is over k vector, so this takes care of all the discrete modes, discrete values of k that k can have, because you place the electromagnetic field in a volume V, and then you impose periodic boundary conditions, and this lambda is basically the sum over the two possible states of polarization. Since this is a quantum field theory, we should not talk about polarization anymore. Rather, this lambda is basically the two spin states that the photon can have. So you can see now the photon picture, the energy eigenvalues. So this is like the number operator, and this Hamiltonian, if you act it on a state, you will get the energy of that state. So if you act it on a state, which is a state representing the number of particles with momentum k and polarization lambda, or spin projection lambda, and then you act it with the Hamiltonian, you will get the energy of that state. So this lambda is the summation over the possible angular momentum projections of the spin angular momentum of the photon, which is 1, along the direction of its linear momentum. So this actually completes the quantization of the electromagnetic field. We have one more field to quantize, and that is the Dirac field. But one thing you should remember, that this quantization of the electromagnetic field is in the Coulomb gauge. We have actually fixed a gauge. But the question is that can we perform this quantization of the electromagnetic theory without fixing any gauge beforehand? And that particular answer to this question is yes, you can do it, and it is called covariant quantization. And we shall actually also look at covariant quantization of the electromagnetic field, but sometime later on. If I have time, I shall try to show you the covariant quantization of the electromagnetic field, where you do not fix the Coulomb gauge by hand from before. You don't fix any gauge in the covariant quantization. So this actually completes the quantization of the free electromagnetic field. One more field that is left that we should quantize is the Dirac field, and we shall do that. But before I go to the Dirac field, I just want you to show a very important thing, that we have already discussed about this thing in our earlier discussions, and this is something related to the complex scalar field. So let us go back to the complex scalar field once again. And if you recall, the Lagrangian density of the complex scalar field is of this form: is del mu phi dagger del mu phi minus n square. This is the Lagrangian density of the complex scalar field. And then we have already discussed that this Lagrangian density basically has a symmetry, and that can be seen from the following fact that if I make a transformation of phi x, of the field phi x, phi prime x, so here please note that we are not transforming the space-time coordinate, rather the field phi gets transformed to phi prime. The functional form of the field is changing without any change in the space-time point. And if I make a transformation of this form, minus I lambda phi of x, and correspondingly phi star will be something like this. Phi star x will be phi prime star x equals e to the power of I lambda phi star x. Then it is actually trivial to see that if you substitute these, so under these transformations, the Lagrangian density will transform like L going to L prime, script L going to this thing L prime, and if you just calculate this by making phi going to phi prime, then you can see immediately that L prime actually remains invariant. This is invariant. So thus we say that the complex scalar field enjoys a symmetry of this form. Where the symmetry transformation is of this form. It has some kind of a symmetry. So this is sometimes you can say that this is some sort of a global gauge transformation. Why global? Because this lambda that I have written here is a real number and it is a constant. It does not depend on the space-time points. And in that sense, it is global. It takes the same. It has the same value at every space-time point. It's a constant and a real number. And we can attach a geometrical meaning to this also. You can see that it is very simple to get a geometrical meaning out of this. You can basically write this equation, this phi prime x. So let me go to the other side of the board. You can write the first equation in the following form. Phi prime, you can write it down as phi 1 prime. I'm not writing the arguments anymore, that the function of x thing. So this is I phi 2 prime. So that is what phi prime x is, where phi 1 and phi 2 are basically real numbers. Let us say that this is classical at the classical level. You don't need to go to the quantum level. So all these are ordinary functions. So phi 1 prime plus I phi 2 prime, that is equal to e to the power of minus I lambda phi x, and phi x is phi 1 plus I phi 2. And similarly, for the phi prime star x, what we shall get is phi 1 prime minus I phi 2 prime, that is equal to e to the power of plus I lambda, and phi star, that is phi 1 minus I phi 2. So we have just written down these two equations, breaking it up into real and imaginary parts. Okay? And now just add these two equations. If you add these two equations, then we will get immediately 2 phi 1 prime, that is equal to e to the power of minus I lambda plus e to the power of plus I lambda phi 1. Then we will get plus I to the power of minus I lambda minus e to the power of I lambda by 2. And from here, is equal to this factor is basically 2 cosine of lambda phi1, and this we can write it down as this is up to minus. If I pull out a minus, then by 2, what you can do is you can write this as minus, this is plus, minus by 2i multiplied by 2i. So this will give us plus 2 to sine lambda by 2. So if you add these two equations, you will get an equation of this form. And from here, you can just get rid of 2, you can cancel the 2, just cancel it. So phi1 prime is basically cosine lambda phi1 plus sine lambda phi2. And similarly, if you subtract these two equations, what you will get is phi2 prime will be minus sine lambda phi1 plus cos lambda phi2. So you can see from this simple calculation that these two equations actually represent a rotation of the vector phi, which you can define it as I cap phi1 plus j cap phi2. It is basically a rotation. If you rotate the vector field phi vector in the xy plane by an angle lambda, then also this theory remains invariant. This is what it says. So it has a rotational symmetry. The symmetry, that transformation that I have written over here, this symmetry transformation, is basically nothing but a rotational symmetry. That is, you rotate the field, the vector field phi vector given by this form, I cap phi1 plus j cap phi2. I cap and j cap are unit vectors orthogonal to each other. And if you rotate in the xy plane or 1-2 plane by an angle lambda, then also your theory remains invariant. So there is a rotational symmetry. So you can attach a geometrical meaning to this. Now let us discuss. The important question is that what if I make this transformation, the symmetry transformation? Here you remember that lambda is a real constant. But what if I make this lambda to depend on the space-time coordinates? Does the symmetry still remain? Does it? So in other words, what I'm saying is the following. Let me just change it. What I'm saying is that suppose I make a transformation. I say that phi x goes to phi prime x, and that is equal to e to the power of minus I lambda phi of x, but this time I make lambda to be a function of x, and x is a 4 vector, so it is actually time t as well as the spatial coordinates. So the question is, if I make such a transformation, is this still a symmetry of the symmetry transformation for this Lagrangian density? The answer is no. You can see it immediately, because if you make this kind of a transformation, this term in the Lagrangian density will remain invariant. But in this term, there is a derivative with respect to x. So this derivative will also hit this lambda, because lambda is now a function of x. So this term will actually spoil the symmetry of the Lagrangian density. So this transformation will no longer remain a symmetry transformation for this Lagrangian density. But, so we have now got the answer to our question, is this a symmetry transformation for our Lagrangian density? The answer is no. But can I make this transformation a symmetry transformation, a symmetry of some unknown Lagrangian density which has a complex scalar field like this? So it is obvious from this, if you want to make this a symmetry transformation, it is obvious that this Lagrangian is not the full story. You have to add something more to make this a symmetry transformation of the full theory. And what is that something more? So let us find it out. First of all, you see from here, what we can do is we can immediately calculate for infinitesimal transformation, we can calculate delta phi of x, and that is equal to phi prime x minus phi of x. Okay? Since the transformation is infinitesimal, therefore I can write this as 1 minus I lambda of x, phi of x minus phi of x. And this will cancel. And therefore, what we get is minus I lambda x. So this is delta phi x under an infinitesimal transformation. Therefore, delta phi star x is under an infinitesimal transformation will be I plus I. Lambda is real, so it will be plus I lambda x, but phi is not real, therefore it will be phi star x. Okay, so this is delta phi of x. Let us now see what is delta of del mu phi of x. Let us calculate that. So delta of del mu phi of x under an infinitesimal transformation. By infinitesimal, I mean that phi going to phi prime x is basically 1 minus I lambda x I x. This is an infinitesimal transformation. So delta of del mu phi of x, that is by definition, this is del mu prime, sorry, del mu phi prime, because you are not changing the space-time coordinates. So del mu remains del mu, and this is minus del mu phi of x. This is what it is. Phi prime, you know, the substitute what phi prime is. Phi prime is basically this thing. This is del mu 1 minus I lambda of x phi of x. That is what phi prime is, minus del mu phi of x. And from here you can immediately see that this term will cancel this term. It's gone. Therefore, this is equal to minus I del mu lambda x phi of x. Now we can see that there are two terms, minus I del mu lambda of x phi of x plus lambda of x So you can see what delta of del mu phi of x is. It is basically the sum of two terms. From the second term, you can see that delta mu phi of x, delta of that is del mu phi of x transforms exactly in the same way as phi x transforms, because delta phi of x is minus I lambda phi of x. Delta of del mu phi of x is minus I lambda del mu phi of x. So that transformation property is quite nice. But what spoils the thing is that you have a term which is del mu lambda, because lambda is not a constant, this term will survive. And therefore we say that del mu phi of x does not transform covariantly. It does not transform in a covariant way, because this term spoils the covariant transformation of del mu phi of x. So with this, we now calculate, with this expression, we now calculate what is the change in the Lagrangian density L. So let us now calculate what is delta L. So delta L, you can immediately see that this term will remain invariant under that transformation. Okay. So we don't. So delta of phi dagger phi. Let me just write phi star here instead of dagger. So you can see that delta of phi star phi, the coefficient, the mass term, that remains invariant under this transformation. So the only change will come from the first term, from the kinetic term, and that is delta of del mu phi del mu phi. That is what it is, and therefore this will be nothing but twice of delta of del mu phi star. Sorry, you are correct. Phi star. So this will be what? This will be del mu phi and delta of del mu phi. Let me actually write it carefully. So let me just write this as mu and this is mu. You can do it anyway you like. So this will be delta of del mu phi into del mu phi star plus del mu phi delta of del mu. That is what it is. And now you can just substitute the value of this thing. So let us substitute what you have got from. So let me show you the full board now. It'll be easier for you. I hope you can see the full board. So what we shall do is we shall substitute this expression here and also here. So the first term, this will be nothing but minus I lambda delta mu phi minus I del mu lambda phi del mu phi star, and then you have the second term which is plus del. So here what again I can do this in this way, just pull right del mu phi, this mu on top, pull this down, this mu downstairs, and then you will get this as del mu phi star. So it will be plus I lambda del mu phi star plus I del mu lambda phi star. So this is what we shall get, and from here you can immediately see that this term and this term cancels. So let me just focus it now. So what we are calculating is delta L, which is del mu phi star del mu phi, the sum of two terms, and we have put in substituted the transformation for delta for del mu phi, which is this. We have put in the transformations. This is what we get. Then two terms cancel, and finally this will be equal to. This will be equal to what? This will be minus. You can write this as del mu lambda, then this is I phi star del mu phi minus phi del mu star. So this is what we shall get. And if I call this term as J mu, then this is nothing but J mu del mu. So you can see that this is the amount. This J mu del mu lambda, where J mu is I phi star del mu phi minus phi del mu phi star. This is the amount by which delta, which actually quantifies the amount by which L is not invariant anymore. So this is the change in L. Delta L is actually this. So this shows that this particular transformation that we have made is not a symmetry transformation of the Lagrangian density L, of this Lagrangian density. It's not a symmetry transformation. But now let us add to this L a term L1, where L1 is given by minus P J mu A mu. Let us add this term to this Lagrangian density. Okay? And let us calculate. Yes.
I can't see.
Huh?
I mean, please side keep the. Okay, okay, it's okay.
Okay, so I will go. You want to see the full board? J is that
No.
expression.
It's okay, sir.
Okay. Let us calculate what delta L1 is. Delta L1 is minus E delta of J mu A mu plus J mu delta A mu. So what we have done in this, when we have added this term L1 to this original theory that represented by given by Lagrangian density L, we have added a term L1, and in the process of adding this term L1 to the original theory L, we have actually introduced a new field A mu. And now what we say is that we give a property to this A mu. Our aim is to construct a theory, a full theory whose change in the Lagrangian density will be zero under that transformation, so that that transformation becomes a symmetry transformation. That is our aim. So we now give a property to this new field that we have introduced as A mu. We say that A mu x under that transformation that we have given transforms like A prime mu x, that is equal to A mu x plus 1 by E del mu lambda of x. So the new field that we have introduced, we are saying that it transforms in this way. So that the change in A mu under the transformation that we have given is nothing but is defined as A prime mu x minus A mu x, that is equal to 1 by E del mu lambda of x. So if this is the transformation property of this new field A mu, so we just substitute it back over here. So this will become what? Minus E delta J mu A mu minus E J mu delta A mu. So you can see from this term that minus E and 1 by E will cancel, and what we will get is minus J mu del mu lambda of x. Okay, and therefore you can see, let me show you the full board once again. You can see that the change in L1 that we have added to the Lagrangian density L, that change in L1, one of the terms J mu del mu lambda x comes with a minus sign, and that precisely cancels the change in delta L. So these two terms get cancelled. This cancels with this term. Therefore, we have now obtained a theory where delta of L plus L1, this theory, if you calculate the change, that is basically equal to minus E J mu A mu. So this theory, if you make a transformation and calculate the change under the transformation for this theory, this will be equal to this. It's still not zero. Okay. Delta J mu. Delta J. This will be delta J mu. Thank you. So this will be delta of J mu. Delta of J mu A mu. But delta of J mu we can immediately calculate, right? Because we know the expression for J mu. Let me write down the expression for J mu. J mu is I phi star del mu phi minus phi del mu phi star. This is what J mu is. And therefore, delta of L plus L1 is equal to, this is equal to minus the A mu, I can put it on top, and delta of J mu, this is equal to minus A mu. You can put the I in front, and then this will be delta I star del mu phi plus phi star delta phi minus delta phi delta mu. We know each of the changes separately. We know all the changes. So let us substitute them. So I just leave it as an exercise for you to do. You just substitute delta phi star because you know what delta phi is. So you know delta phi star. You also know what del mu phi is, delta of del mu phi is, and also delta of del mu phi star is. We have calculated those things. And if you substitute all the expressions here, then ultimately what you will get is the following. You will get this will be equal to minus, just do this calculation and check it for yourself. It will be minus 2e phi star phi a mu a mu. So this will come out to be this minus 2e phi star phi del mu. No, I think it's not the correct expression. This will be a mu.
Sir, from where does next mu comes?
Just a minute. I will come back. I will come back to you. A mu, this will be del mu lambda. Please ask the question.
No, it's okay.
So what we are doing is, okay, I will just focus it on one now, so that it becomes better. So what we are calculating is L plus L1 change in that, okay, and that comes out to be, we have actually calculated it to be minus E A mu delta of J mu. We know what the expression of J mu is. J mu is this that I've written on top. So we calculate delta of that, delta of J mu. So that is basically this. And what you now do is you substitute the expressions for delta phi star, delta del mu phi, delta phi, and delta del mu phi star. We have calculated each of these for infinitesimal changes. Calculate those things, and if you substitute those things here and simplify, the final result will be minus 2e phi star phi a mu del mu lambda. This is what I am saying. Is this okay? So you can see that delta of L1, L plus L1 is basically this. So now our aim is to add, our strategy is to add some more term so that we can actually cancel this change. And let me now add some term which is E squared phi star phi a mu a mu. Let me add this term and calculate the change in this term. So this will be E square. See, the change in this term will be the sum of two terms, the change in this term multiplied by this, plus the change in this term multiplied by this. But the change in this term is 0, because it is phi star phi. Therefore, it will be phi star phi change of a mu and a mu. in this term. But this, you can write it down as twice E square phi star phi A mu, write A mu like this, delta A mu. Okay? But what is delta A mu? You know what is delta A mu? Delta A mu is 1 by E del mu lambda. So therefore now you get this is 2E phi star phi del mu lambda. So now you can see that if you add L2 to this term L plus L1, then the change of this full thing L plus L1 plus L2, the change in L plus L1 was minus of this thing, and the change in L2 is plus of this thing, and therefore this term actually cancels this term, and therefore the change in L plus L1 plus L2 is 0. And therefore we now have a theory where our full theory, which remains invariant under the transformation that we have written down earlier at the beginning of this lecture, is the following. We write down the full theory as LT, and that is basically L plus L1 plus L2. L is what? L is del mu phi star del mu phi star phi minus m square phi star phi. This is what L is. What is L1? L1 is minus E J mu A mu. What is J mu? So it is I phi star del mu phi minus phi del mu phi star. And then you have an A mu. So this is what J mu A mu is. This is what L1 is. And then you have L2. And what is L2? Plus E square phi star phi A mu A mu. This is your full theory. So we have now written down a theory which consists of a field phi, complex scalar field phi, and a field mu. This full theory, this field mu is actually coupled to the field phi by this interaction. There is an interaction between the field mu and phi. And also you have this term mu is mu coupled with phi star phi. This theory is actually invariant under the transformation that I have written down at the beginning of the class, and that transformation is said to be a gauge transformation. Why? Because that lambda is now a function of the space-time coordinate. So it is a gauge transformation. And under that transformation, this full theory becomes invariant. And you can further simplify this theory, this Lagrangian. One thing that I should mention is that the field that was needed to make this theory invariant, it transforms like a gauge field, because mu has the way in which mu transforms. It is a vector field first of all, because it has one Lorentz index, and it transforms in actually the exact way in which an electromagnetic field 4-vector potential transforms. So we can actually identify this mu field as the electromagnetic field. And you can see that if I want to write down a theory which is invariant under local gauge transformation, then we need to introduce the electromagnetic field. It comes automatically. You need to add a vector field which has this property of gauge transformation. And also, and another thing is that it couples to this complex scalar field in this following way. You also get the interaction term between the two. So far we have been talking about free fields. Now in this case we have an interaction term, and the interaction is between the complex scalar field and the electromagnetic field. And one more thing, you can add another term to this. You can define a field strength tensor as F mu del mu a mu minus del mu a mu, and you can check that this f mu nu, this is a second rank tensor, is antisymmetric under mu nu, and this field strength tensor is called a field strength tensor, is actually invariant under the gauge transformation that we have already written down for this electromagnetic field a mu. You can check this. This is immediate, and you know if this is a field strength tensor, then into this theory you can add another term 1/4 f mu nu f mu nu. This is the kinetic term for the electromagnetic field. You already know that this term actually gives this term remains invariant under the transformation by which phi transforms and A transforms. So this only has A in it. So this f mu nu is itself invariant under the transformation by which A mu transforms under gauge transformation, and therefore f mu nu this is also gauge invariant, and this is a kinetic term. This gives rise to the Maxwell equations, and this is the full theory that you have. So this is basically electromagnetism coupled to a complex scalar field. And this full theory is actually invariant under that local gauge transformation that I have mentioned. And that local gauge transformation, you can actually immediately see that the transformation that I have given you e to the power of minus I lambda x, phi prime x is equal to this thing. So that e to the power of minus I lambda x, that is an element of U1 group. So it has a U1 gauge invariance. Okay, it is this electromagnetic. So you can see that this complex scalar field coupled to electromagnetism, this full theory has a U1 gauge, local U1 gauge invariance. So this is something very interesting. And one more thing before I finish this, you can immediately see from here that you can combine these terms in the following way. You can combine it as d mu phi star d mu phi star minus m squared phi star phi minus the Maxwell term that we have already learned. So this is d mu phi star minus m squared is the mass term. So you can combine this term, this full term, and this term into this term. What is capital d mu? D mu phi is basically del mu plus I a mu of phi. And what is d mu phi star? It is del mu minus I e a mu of phi star. This derivative that I have defined now, this is called the covariant derivative. Why covariant derivative? Because you can immediately check that the following thing. You can immediately check that d mu phi transforms in a covariant way. That is, d mu phi, to take a variation of that, this will be minus I lambda d mu phi. So now you see that this is the derivative, not del mu phi. Del mu phi does not transform covariantly, but d mu phi indeed transforms in a covariant way, and therefore this is called the covariant derivative. And this you have already learned in quantum mechanics also, where you have a charged particle moving in an electromagnetic field. What you do is that in the Hamiltonian you replace P by P minus EA, that is a minimal coupling, and that is actually the covariant derivative. You can see that this is P, nothing but something like P minus EA. So this actually, so P minus EA is basically a covariant derivative. And you see that this is called covariant derivative because it transforms in a covariant way. You can immediately check. You just put in the definition of d mu phi. You put what d mu phi is, put in the variations of del mu phi and delta mu and delta phi separately, and you will see that you will get this result. So this actually shows this full lesson actually tells us how to construct a theory or how to construct the action of a theory by using symmetry principles. So if you impose or if you say that my principle is that I want to construct a theory which will remain invariant under such a kind of a transformation that I have made. And what you ask, what is the theory? And this is the way you construct the theory. This is the full theory which remains invariant under the transformation that I have given. So now the transformation that I have written down earlier with lambda as a function of x is indeed a symmetry transformation of this theory, because under that transformation this Lagrangian density remains invariant. And you can see that in this way, the way in which the action is constructed, you also introduce you need to introduce new fields, and these fields get their interpretations automatically from their transformation properties. So this is also something important. For example, here mu it was needed to introduce a vector field mu with a particular transformation property, and we immediately identified that this transformation property coincides with that the electromagnetic field that we have already learned. So this is a gauge invariant gauge transformation property that we have introduced. So I would like to end at this point, and from tomorrow what I shall do, I shall start to quantize the free Dirac field. Okay. So tomorrow we have some certain amount of time. So if you have some questions, we can address those questions in tomorrow's class, because we have lots of time tomorrow. So thank you very much for today. Please go through this thing.
Sir, actually I have a question.
Please.
Yesterday you started with the quantized form of the vector potential A.
Yes.
But is there any derivation to get that form particular?
The quantized form for what? The vector potential. Actually, we gave a derivation, right? We actually argued how you can expand the classical electromagnetic vector potential, the vector field, in terms of the normal modes of the wave equation satisfied by the free vector potential. So we expanded it see, the procedure is exactly similar as we do it for the real scalar field and the complex scalar field. We follow the same procedure for all the fields. You have to expand the full field, the classical field, in terms of the eigenfunctions or the normal modes of the wave equation, or in case of the complex scalar field, it is the Klein-Gordon equation. In case of the electromagnetic field, it is a wave equation. So you expand it, and now when you elevate, you go to the quantum. When you go to the quantum regime, then what you do, you elevate the status of those functions, of those fields, which are functions in the classical case, to operators, and then since they are operators, you still expand them in normal modes of the classical wave equations, expand in terms of those appropriately placed in some box with the periodic boundary conditions imposed and so on. You do that, but since now the left-hand side is an operator, you need to have an operator on the right-hand side, and those are the creation and annihilation operators. So we have actually derived it. Okay.
Okay, sir.